Okay, let me solve two more examples from fixed point and Newton method. The first one is an equation, example number 3, for example, and the first one is consider the equation f of x equal to x squared minus tangent of x plus 1 equal to 0. We want two things, 1 and 2. Number 1, we want number of roots. By MATLAB. And the second one, the roots by fixed point and Newton methods. Okay, now let me solve the problem. First of all, we have to find the number of roots by MATLAB. It's very easy. We have to just plot the curve of the two equations. One function is x squared, and the other one is 1 plus tangent of x. Look at here, x2 equal to tangent of x minus 1. So if we get y1 equal to x2 and y2 equal to tangent of x minus 1, and let x change from minus 1.5 to 1.5. Okay, let me plot these two curves and find the number of roots. So I'm here now. CLC for cleaning the workspace, and let me write x equal to minus 1.5 step 0.01 to 1.5. okay, and y1 equal to x squared and y2 equal to tangent of x minus 1. Now we plot x and y1, x and y2. Look at the plot. Yeah, this is the plot. The intersection, I mean here, is the root of the function. So there is just one root. It seems there is just one root, a unique root between 1 and 1.5. So I have to find this root by fixed point and Newton method. So let me find the suitable suitable G for the fixed point method. Consider x squared equal to tangent of x minus 1. This get x equal to g of x equal to square root tangent of x minus 1. But this is not acceptable. Why? Because, for example, if you consider g 1.1, okay, it will be square root tangent 1.1 minus 1, okay, and this will be 0.9299. Okay, let me see. Yeah, I'm right. By this figure, we can find out the root is between 1 and 1.5. Okay, so we get the interval 1 and 1.5. Okay, and this number is not inside the interval, so this g of x is not acceptable, and we have to find another one. Now, let me consider this one. Tangent of x equal to x squared plus 1 from this equation, and this gives me x equal to g of x equal to arc tangent of x squared plus 1. Okay, this function has to have two properties. Property number 1, this is okay. Why? Because if you consider this interval, g of interval 1 and 1.5, this will be inside 1 and 1.5. You can find it easily, it's clear. And about the second property. What's the second property? The second property is something about the derivative of g. So we have to compute g prime of x, g prime of arctangent x squared plus 1 will be 2x over 1 over x squared plus 1. And we know in the interval 1.1 and 1.5, this is less than or equal 2 over 4 plus 1 will be 2 over 5. If we call it L, this is less than 1. So the second condition, the second property is also okay. So we can define xn plus 1 equal to g of xn equal to arc tangent of x squared plus 1 xn squared plus 1. Now let me write something more, and if we want to use the Newton method, we have to define the function something like this: f of xn over f prime of xn, and this is xn minus, the first one is x squared minus tangent of x plus 1 over 2x minus secant squared of x. In fact, all of these should be xn. So we have two sequences. This sequence is for fixed point. This is for fixed point. And the other one is this sequence. This is for Newton method. So let me implement both of these sequences and find out the solution and in fact compare the rate of convergence in two cases. So let me close this figure and open my editor. This is fixed point. Let me consider this sequence y equal to arc tangent x squared plus 1, and we start from a number in interval 1 and 1.5. For example, 1.2. Okay, so if we run it, we can find out the solution or the root of the equation is 1.17 in 11 iterations. Now, let me try the same equation in Newton method. This is the main equation. Y is x squared minus tangent of x plus 1. And this is the derivative 2x minus secant of x squared. Okay, let me save and run. The solution, let me see what happened. Maybe something wrong in initial value. Yeah, x1, it is not correct. It should be 1.2, same as the fixed point method. And now we run it. The same route with just 4 iterations. So, in fact, the Newton method is much faster and much better than fixed point method. This is the first problem that we solved. Okay, the last equation that I want to solve, and maybe the last one of this kind of problem, exercise number 4. Let me write this problem first. Solve f of x equal to e to power of x sine of x plus 25x plus 1 by fixed point and Newton method. Okay, so let me first find the number of root, in fact, by MATLAB. First of all, okay, let me clear the screen and let x from -1, step size 0.01 to 10. And look at here, we have to write something like this: e to power of x sine of x plus 25x plus 1 equal to 0, and this gives sine of x equal to minus e to power of minus x times 1 plus 25x. So if we consider this one y1 and this one y2, and we plot y1 and y2 and investigate the intersection of the curves of y1 and y2, we could in fact find the number of roots. So I consider y1 equal to sine of x and y2 equal to minus exponential minus x times 1 plus 25x. Now let me plot x and y1, x and y2 in the same plot. So if you have a look, you can find a 0 here and something here and maybe something here, and it will be continue in the right hand side, in the right side of 10. So let me enlarge this point a little. Look, the first 0 is between -1 and 0, so it is negative. Yeah, or maybe here. Consider here, there is one root here and maybe one root here. So there are lots of roots because sine is a periodic function, and for this function we have several roots. Now let me try to solve the equation by fixed point by finding the suitable function g of x for the interval -1 and 0. Okay, first of all, we have different and several different choice for g of x. Let me start by e to power of x sine of x plus 25x plus 1 equal to 0, and we compute e to power of x from this equation. E to power of x is minus 25x plus 1 over sine of x, and this gives x equal to g of x equal to ln minus 1 plus 25x over sine of x. Okay, so consider the interval minus 1 and 0. Let me write the interval here, minus 1 and 0, for example. This is the interval for the first root in the negative part of the axis, x-axis in fact. So for this function, I say this function is not acceptable. Why? Because if you compute g of minus 0.5, okay, it will be a negative number. It will be a negative. No, let me say g is minus 0.5. 5 is not defined. In fact, if you put minus 1, minus 0 here we will have 11.5 over sine of minus half, and it will be a negative number. So ln of logarithm ln of negative number has not defined. So this is not acceptable. Okay. The other choice maybe can be like this: sine of x equal to minus 1 plus 25x over e to power of x. It will be minus e to power of minus x times 1 plus 25x. Okay? And this gives x equal to g of x equal to sine inverse minus e to power of minus x 1 plus 25x, and this is also for g of 0.5 not defined. So this one is also not acceptable. The last choice that is a good choice is x equal to minus 1 plus e to power of x sine of x over 25. This is okay. Why? Because if we call this function as g of x, g of minus 1 and 0 will be in minus 1 and 0, and this is in fact the first property. And the other one, if you compute g prime of x to form 1 over 25 times e to power of x sine of x plus e to power of x cosine of x, it will be 1 minus 1 over 25 e to power of x times sine of x plus cosine of x, and this is less or equal something L less than 1. So g of x is acceptable, and we can define xn plus 1 equal to g of xn equal to minus 1 over 25 e to power of x sine of x plus cosine of x. In fact, all of these should have xn. This is the sequence the suitable sequence for the fixed point problem. But if we want to generate a sequence for Newton method, we have to use something like this. And this is xn minus here we have to put f of x. What's f of x? It is this one, e to power of x sine of x, e to power of xn sine of xn plus 25 xn plus 1 over 25 plus e to power of xn sine of xn plus cosine of xn. This is the clue. Now, let me implement both of these equations, for the methods, in fact, in MATLAB code that I have written before. Now, let me first show you the fixed point. Let me comment this one. This is the suitable sequence for the, in fact, fixed point method. Minus 1 over 25, 1 plus exponential of x times sine of x. Exactly something like this. No, let me see. Something wrong. Something wrong. Yeah, here. Here, yeah. Sorry, my table is very, very small and I have lots of problem here. This is not true. I have to clean this part and define g of x like this one. This is the correct sequence. Minus 1 over 25, 1 plus e to power of xn sine of xn. This is true, and this is for the Newton method. Let me back to the program here, and now you can see here minus 1 plus exponential of x star sine of x over 25. And let me start by a number, for example, minus 0.5, a number in the interval minus 1 and 0. Let me save and run by pressing F5. The solution is minus 0.038518. Okay? Now, if I change, let me first try with the Newton method. Here, let me comment this line. Consider this as y and comment this one and consider this one as y prime. Okay, and let me start with minus 0 here, minus 0. Let me save and run by pressing F5. The solution is exactly the same, but in 4 iterations. Okay, we had here some different roots in the different intervals for the equation. For example, here we have a root between 4 and, for example, 5, or 4 and 6. Yeah, let me try the same. Let me try here for fixed point with starting point 4. And let me try to run it. We again get the root, the negative root. Okay? But if I try the Newton method, with the new starting point 5, for example, and I run the program, I get a new root 4.79. It's good. So by Newton method, if I choose the starting point near to another root, I can get another root. Okay? Now, let me have a look to the question here. Something, another root is between, for example, 8 and 10 in this interval, or 9 and 10, something like this. Let me try first the fixed point, for example, with 8.5 and run the program. Again, we found the previous root. Okay, now if I try with Newton method with this new starting point 8.5 and I run it, I get 8.5. Maybe if I change, it's a little better. Let me put, for example, 9, and let me okay, now it's 9.44. This is another one. And in the same way, I can change, for example, something like 25. Let me try it. You can get the other root here. Okay, and so on. So this is the last example for fixed point and the Newton method, in fact, for finding the roots of fixed point and Newton method. And in the next lectures, if I want to solve some problem, I will try to solve some analytical problem and some example that you need to prove, for example, something. Please subscribe my channel and introduce my channel to your friends. Thank you.